Through the mid-1960s, after the successful completion of the Mercury and Gemini programs, NASA had made more ambitious plans even beyond the increasingly vocal goal of landing men upon the surface of the Moon. NASA was out to establish a permanent human presence in space and make true the dreams of over a century of science fiction writers. Of course, reaching out for space is something humankind has dreamt of for as long as we saw stars in the sky, and with so many great successes in the massive 1966 budget, it seemed almost certain that the future would be a bright one for NASA, and human spaceflight in general. Before even the first Apollo spacecraft had flown, NASA had explored numerous other possible uses for Apollo and Saturn hardware. These developments initially began with the concept of maintaining longer duration lunar bases by simply upgrading and adapting the vehicles already in development, potentially leading to surface stays as long as 90 to 180 days. Another ambitious proposal was sending an Apollo spacecraft on a manned flyby study of the planet Venus, utilizing the spent Saturn IVB stage as a wet workshop. What this meant was, once the S-4B booster completed its burn into the flyby maneuver, its remaining propellant would be purged, and the internal space could be used as a habitable workshop and as a living space for the crew during a long journey, to be discarded only when the spacecraft approached Earth for re-entry. Less ambitious but equally appealing to the scientific community was the Apollo telescope mission. Launching in a similar fashion of the Apollo lunar missions, however, instead of the lunar lander, a specially designed solar observatory telescope would be tucked in where the lunar module would be, for the command module to dock with and operate. The telescope module itself even providing some pressurized habitable volume to give the astronauts space to work for the 3 to 4 week mission. NASA had approached Congress with its budget proposal, wishing for its 1967 budget to include an additional $450 million to be allocated to what they called the Apollo Extension Series. But despite all that NASA had accomplished, the boost to public opinion, and the sentimental value of reaching late President Kennedy's goal of the Moon, Congress allocated only $42 million to the extension projects, and even cut back the following year's budget overall. And for the first time since NASA's doors opened, their budget had shrunk. Though still a substantial number, it had begun a pattern of budget freefall that would persist for the next decade. Even worse, in January of 1967, the worst thing possible had happened. The 3 men of Apollo 1 lost their lives in a fire, crippling NASA's morale and shattering the support that many congressmen had afforded them. It was difficult enough to convince Congress to allow the Apollo moon program to continue, but from here, it became an all-out battle for NASA to get any of its new project proposals through, much less any budget to see them through to completion. The Apollo program as is was allowed to continue, as work focused on making the command module safer and more reliable, but as the turn of 1968 came about, and not a single manned flight of Apollo had yet flown, the budget suffered additional cuts. Long-term lunar base proposals were rejected, longer stays upon the surface were cut back, the Venus flyby proposal was all but laughed off, and a halt on further Saturn V construction was implemented, locking NASA into ending the Apollo lunar program after Apollo 20. In this, there was little NASA could do but press on with their current plans. But this also meant that many of its 400,000 employees would be losing their jobs after the moon landings were underway. In an effort to keep from massive layoffs, NASA consolidated its future proposals under a new umbrella called the Apollo Applications Program, as well as the Apollo Logistics Support System Office. These branches were tasked with the singular responsibility of finding ways to adapt the remaining Apollo hardware into viable programs beyond lunar landings. Wernher von Braun also followed this sentiment, as he was insistent on finding ways to keep his employees working, even after the final Saturn V's would be built. Though many of the proposed projects were cancelled, many of the concepts behind them remained viable. The solar telescope and the workshop, for example. In fact, even before manned spaceflight began, von Braun had championed the idea of an orbiting space station, intended to be a waypoint for journeys to the moon. His idea was far grander, of course, requiring several segments of a large rotating ring structure to be built in orbit. But when it became clear that this idea would not come to pass, the remaining hardware of Apollo presented a unique opportunity. While all Saturn V's were currently spoken for, a couple Saturn 1B boosters were left available when some of the low Earth orbit and lunar module test flights were cancelled. In this, the Venus flyby proposal was reworked, reviving the wet workshop idea, using the second stage booster as a habitable workspace once its remaining fuels were vented upon reaching orbit. As with all of von Braun's ideas, he had a larger proposal in mind along with it, using the second stage of a Saturn V as the wet workshop, while retaining the third S4B stage as a dry workshop, that is, a prefabricated habitable module that did not require any fuel purging, and would subsequently open up the S2 empty hydrogen tank for a much larger workspace and habitable volume. This, however, would have required another Saturn V, and at this point, one was not available for use, and Congress would surely not approve any budget increases to build another. By this time, contracts had been sent out to Douglas, Grumman, and McDonnell Aircraft in developing the spent S4B station conversion. Also at this time, the Apollo Applications Program had a competitor, the United States Air Force, and their Manned Orbiting Laboratory, or MOL, program. Unlike AAP, MOL utilized Gemini hardware, including the Titan 3C booster, with a large habitable module attached to the base of a standard Gemini, accessible through a hatchway cut into its heat shield. Even as competitors, the two programs cooperated in technology, as they had fundamentally the same goals overall. But even though the Titan 3C was far less expensive than the Saturn 1B, it was determined that MOL was not large enough, and it would add unnecessary costs to convert Apollo to function with the Titan hardware. Come 1969, MOL was officially cancelled, and all hardware and development shifted over to AAP, and all program's intended astronauts were brought in as NASA's Astronaut Group 7 later that year. By this time, the goal of the moon had been reached, and the world celebrated when Neil Armstrong and Buzz Aldrin walked upon its surface. But also by this time, NASA's budget was roughly half of what it was in 1966, and still dropping. NASA was determined to continue with its post-Apollo plans, and around the same time as Astronaut Group 7 was announced, the new combined McDonnell-Douglas Aircraft Company was given the contract to convert two existing S4Bs into a workshop configuration. In this configuration, the internal volume would consist of mounts for equipment and experiments that would be sent up to the station after it was placed in orbit and the excess fuel purged, along with graded flooring to allow the fuel to pass through while its launch was underway. In January 1970, McDonnell Douglas received its first Saturn IVB to convert into a mock-up of the new configuration. That same month, NASA held a contest to name what would be its first operational space station. By February, that name would finally be announced: Skylab. 1970 would also present a new development, as the mission of Apollo 20 was officially cancelled. In this, a Saturn V had suddenly become available. While this would have made von Braun's proposal of a larger station built of a Saturn IVB and S2 stage possible, too much money and time was put into the wet workshop, and this larger plan was rejected. However, it did allow for the wet workshop to instead be a dry workshop, launched atop the two-stage Saturn V. This meant there would be no need to purge fuel from the station, and allowed for the station itself to be outfitted to a greater degree before launch, eliminating the supply mission, presenting a clear savings in cost. Still, many aspects of the wet workshop design had already been developed, thus stayed with the remainder of the program. Things like the graded flooring and a large hollowed-out interior. And it was this that made Skylab stand out from every spacecraft and orbital facility thus far, even by Russia's Salyut space station. Room to stretch out and live for long periods at a time. In fact, habitability was a major concern in Skylab's development, offering staterooms for the crew, a dedicated shower, a wardroom for meals and relaxation, and windows to look out on the Earth below. Habitability was such a concern that the previous year NASA sent one of its scientists on Jacques Piccard's Ben Franklin submarine expedition. The journey that would drift through the Gulf Stream at a depth of 1,000 feet, not only to study the ocean floor, but study the effects of humans in enclosed isolation for 4 weeks. This is something that NASA was particularly interested in, especially Werner von Braun, who personally selected the scientists who would participate. Beyond accommodations, one of the most important things the astronauts wanted in this new space station was a new type of food. In fact, the food that was provided through Apollo was particularly disliked, so much that a NASA volunteer who tried living on it for 4 days found it to be an intolerable experience. How men of Apollo lasted the endeavor is anyone's guess, but it was clear that those who were going to participate in Skylab wanted this issue fixed, and wanted food that was actually edible, not merely scientifically adequate. As the development of the station continued, another Apollo applications project was merged with it, as the orbiting workshop presented an opportunity to also utilize the solar telescope, originally intended to launch alone with an Apollo CSM. This way, it could remain for longer periods of time, have a permanent facility to be mated to, and to be used by multiple crews. This became the Apollo Telescope Mount, built out of the basic structure of a lunar module's descent stage, with 4 large solar wings to give Skylab its familiar X shape. It would remain in a vertical position along with the station's length during launch, and once deployed, pivot to a 90-degree position and deploy its wings. Attached to the top of the S-4B station tank was a smaller cylindrical module that served as both a docking adapter and an airlock between it and the station itself. This multiple docking adapter had something that no other station had at the time: a second docking port. Though Skylab was never intended to be met by multiple crews at a time, the second port was available should something happen to the Apollo CSM that carried its crew on board, allowing for a rescue craft to dock with the station and retrieve them, without having to jettison the derelict Apollo, in case something of it could be salvaged or even repaired. By 1971, the missions of Apollo 18 and 19 were cut, as were all remaining planned Earth orbit Apollo missions. This left 3 unused Saturn V's and 5 unused Saturn 1B's. This worked out well for Skylab, as the station itself could boost into orbit on a Saturn V. The S-1Bs could take Apollo command modules into orbit to rendezvous and dock with it. In this, one S-1B and command module was tasked specifically to be a standby vehicle should rescue ever become necessary. What the multiple docking adapter lacked, however, was a method for transferring fuel and fluids from a spacecraft to the station, but this puzzle would later be solved by Russia and eventually implemented on the International Space Station. But such plans were so far in the future that NASA had dared not even dream of them. And first, they had to prove they could operate a station in the first place. May 14th, 1973, the day finally came. The unmanned workshop sat on the pad for the first NASA spacecraft launch in nearly a year. The 5 bellowing engines of the final Saturn V rocket ever to lift off from Kennedy Space Center ignite.
We have ignition sequence has started. 4, 3, 1, 0. And we have a liftoff. The Skylab lifting off the pad now, moving up. Skylab has cleared the tower.
All staging events occur properly, and after jettisoning the protective shroud and separating from the Saturn II booster, the station settles into orbit in what appeared to be a trouble-free launch. Then ground controllers began to see readings they were not expecting. Electrical power generated by the solar wings was almost nil, and temperatures inside the workshop began to rise, and rise fast.
Inside the vehicle, it got up to 150, 160 degrees. It's in danger of melting such that the pressure will cause it to split and go apart, a rupture.
Suddenly we were facing a damaged Skylab, and we didn't know what the problem was. was obvious that we were not going to launch the next day, and we had serious problems to work on.
No one knew it at the time, but during ascent, one of the external hull panels of Skylab had torn off, exposing the internal skin to direct sunlight. Further, as the paneling tore off the station structure, it had also ripped one of the solar wings completely off, and debris had left the remaining wing pinned, only a small bit of panel surface exposed. But power was being generated, so obviously the panels were working. They were simply not deployed. Still, the temperatures were of primary concern, for if the hull were to rupture, the station would be rendered useless. Controllers had to tilt the exposed section away from the sun to keep the station from burning up, but in doing so, the exposed surface of the trapped solar wing could no longer generate power, and the station would die.
And it was this constant battle between these two extremes that we had to solve and fight and get a handle on.
Mission Control's bottom row, nicknamed the Trench, handle navigation and guidance. It is their job to control the station, maintain its position, and keep it pointed in the right direction. However, with the damage to Skylab, they suddenly found themselves placed with aspects of the station they were not used to controlling. It was not the mathematicians or trajectories that guided their actions, but the physical conditions of the craft and its onboard systems.
In the Trench, we were dealing with radar tracking data, guidance systems, software, things like concepts.
It is up to the guidance officers to orient Skylab in such a way that its exposed skin was not exposed to too much sunlight, while still being able to generate power from its panels. But its primary method for determining orientation was the sun, and once the station was tilted away, it lost the one thing its navigation system needed. For this, the controllers in the Trench found themselves instead relying on the second row, systems. Mathematicians used to precise calculations, instead turning over control to engineers who do not think with the same mindset. And the man who got principal responsibility for orienting Skylab in a proper position was ECOM, Electrical, Environmental, and Communications, and manning this station was the man who played a major part in saving both Apollo 12 and Apollo 13, the steely-eyed missile man himself, John Aaron.
Normally, since I was a system engineer, I didn't have anything to do with controlling the edge of the vehicle. I mean, that was what the Trench did. Well, as soon as we pointed off the sun, the Trench didn't know where the vehicle was.
It became his job to look at the internal temperatures and the power being generated, and use those readings to estimate how far to tilt the station and in what direction, then forward those commands over to the Trench.
And so we'd tell flight, pitch us up 15 more degrees, and we need to roll left 12. We'd call out those orders. The guidance officer would kind of look at us and say, okay, and send the commands up.
86 degrees, max elevation.
The degree of improvisation was incredible. We innovated solutions that were so far out in left field that it was a leap of faith for one controller to trust another one that they knew what they were doing.
And that was a cultural shock to the Trench when the ECOM started guiding the vehicle. And I'll never forget, I believe it was the guidance officer who stood up. He looked up, come up with the console, and he says, ECOM, tell me something. Do you know what the hell you're doing? I said, just compute the commands and send them up. We'll be all right.
It took 2 weeks of patience, trial and error, and sheer frustration, but it worked. Temperatures remained stable, and just enough power was being generated to keep the station from dying. But it's not over yet. There was nothing more that could be done from the ground. The only way to get Skylab back in a full functioning condition was to send astronauts into space to physically repair the damage, and physically unjam the stuck solar wing. And with this, the station's first crew would become the first space repairmen in history. But that's a story we'll save for the mission itself, when the man whose Apollo mission John Aaron had saved commands the first American space station crew, and we will have that amazing story in 2 weeks' time. For now, it is the tremendous efforts of engineers and flight controllers that we recognize, The fight to keep Apollo, if not the entire NASA program, alive, a testament to the wonderful piece of engineering that would eventually become one of the greatest platforms for studying the effects of spaceflight on the human body and revolutionizing our understanding of the Sun. Skylab is certainly one of the more forgotten pieces of NASA, but its contributions on its ever-shrinking budget were vast, becoming the first step that would shape NASA's future. That first step taken this week in space history.